Yeah, this is a very interesting topic. Maybe I'm not prepared enough, but please follow carefully. Just if you need to stop me anytime, you can do that, because I want you to follow to the end. It's I think it's a beautiful story. I got my PhD recently in physical chemistry, and this is totally different topic. But I'm excited about this. From simplicity to complexity. I had a hard time to pick this topic. Let's get started. When you want to study the dynamic of a system or evolution of a system in time, you need to somehow either calculate the energy, and then from that you can get force, and force is the first derivative of energy with respect to displacement. Or you can dump some energy in your system as temperature. Some systems are well known. You can have force field, and again you can calculate force, and from that you can study the dynamic of the system. As you see here, there's pointer. Okay, force is connected to position and time, so you can see how your system moves in space within time. So the equilibrium of the system is when there is no force on your system, and that can be also interpreted as when you have all the existed energy is dispersed in your system, and the dispersion of energy is shown with this guy. This thermodynamical term is called entropy. Many of you familiar with that, but let's call it for simplicity disorder. So before equilibrium, delta G, this is another term that's called free energy or maximum work you can get out of the system. That guy is negative, and that's the driving force of the system before equilibrium to reach the equilibrium. But once you get to equilibrium, delta G is 0, and your system is not doing anything macroscopically, so it's kind of dead. So for delta G to be negative, either delta H, that's enthalpy, it's called enthalpy, so delta H should be negative, meaning that your system should release some energy. Or this delta S, as we call it, disorder, so your system needs to increase disorder. So if these two conditions, either of them are, if you have one of these two or two of them, you can have negative delta G, and your process is spontaneous or natural. But you see in nature, there are a lot of things that they decrease disorder, but they still happen. They are natural. And one of the very good examples is life. So in life, you have decrease of entropy or disorder, but yet it happens. And that's because there is another restriction for that. The second law of thermodynamics, when you have isolated system, the entropy of your system can decrease as long as that leads to an increase of the entropy of the environment. So that's how life can form. So let's put this in better words from Schrödinger. He's actually one of the founding fathers of quantum mechanics, and he has a book. It's called What is Life? It's a very good book. You can get it for free so there is a link in Wikipedia. It's only, the version I got, I think it's only 32 pages, and it's very short and sweet. So I just borrowed some quotes from him. So living organisms are highly structured systems. We know that they are actually the most highly structured system that we have or we know of. And the ordered structures on larger scale are due to chaos in small scale. And that's because the foundation of everything, or the fundamental particles are obeying quantum rules, which is all probabilistic. And when you have less number of atoms in the particles, you have more randomness, more probabilistic nature. And this one, I want to read it. Living matter evades decay to thermodynamical equilibrium by maintaining negative entropy in an open system. That's very important. That's how life can form. To put it in equations again, delta G is negative, so the process happens, but they avoid reaching equilibrium. And with that, they can increase the entropy or disorder of the surrounding. So if you want to interpret that, we can say life cannot be isolated, or life cannot be formed in isolated systems. Another thing is life has to make mess. So we are big messing machines, in fact. Okay, so here I just made a comparison between just natural evolution, natural processes, and computer simulation. So many of us, when we are doing computer simulation, when we do optimization, we are actually somehow doing, we are making an evolution in a system. So we start with initial simplicity, and then there we introduce some forces on the system, acting on the system. And so then you have self-repeating, self-organizing, and that in simulation terms is, you have, for example, different simulation, you have self-consistency, or feedback loops. Whenever you have feedback loops, it's a kind of self-repeating. And you might be familiar with these terms: interference, overlap, coupling. They're all the same concept. And then you get to complexity. And complexity, you can represent it by this: superposition, chaos, probabilistic. And then you have evolution, or natural selection, mutation, some people say. So when you do optimization, you actually say, hey, I'm going to just keep this coefficient because it optimizes my system, and then ignore the other one, or amplify one and then decrease the weight of the other one. So that's actually kind of natural selection. I mean, it's not natural, but you're just picking. And then that can be represented with emergence, decoupling, iteration. And then at the end, when you get to equilibrium, your system becomes simple in a sense again. And so you have equilibrium, you have collapse, in terms of if you have working with, for example, quantum mechanics, collapse of wave function, and your system becomes deterministic again. And just want to read this again. there are some quotes, I think they are important. Evolution is blind. It's an emergent effect of mutation and natural selection. Maybe a good example for this is a stock market. So some small changes, very random, they can change the whole market. And that's another, that's exactly how natural selection or evolution works. It's completely right, it's blind, but yet it just changes the whole thing according to probability. And so, but there are three main questions we have. Is this process reversible? At least it's not in simulation. Is there any interactive force with our system? Again, in simulation, I don't think so. But we can change the sometimes we need to, after we see the result, we can go back and remodel our system, redesign it. Another question is, so again, if you introduce your forces or laws for the system, are they evolve in time? In simulation, you can do that, but how about in nature? I just give you two examples, two schools of thoughts. One of them is this guy, James Gates. He came to our school a few months ago. He gave a talk about finding the computer codes in the fabric of universe. I didn't get anything from his talk, but he was asked. So he's a string theorist, and he said when you basically work with this equation, pass them through light cones, you get computer codes. Okay, he's a famous guy, so we believed him. But he was asked, are you saying that we are living in a matrix? And what he answered was, okay, yeah, that's a probability. But that's not scientific, because we cannot test that idea. But what he answered, he said, there is another probability that we are one of the probabilities, we are one of the universes, or we are living in one universe. I mean, we have multiverse, and then we are one of the probabilities that we have like computer codes in a universe. Okay. So that's actually the main, I think is the main. I'm not a physicist, so I try to be more careful when I'm using these terms, but I think the main stream of physics is that. So whenever they're trying to explain, why these forces in nature are so tuned, why we have these physical constants, the answer is, so maybe is one of the probabilities, one outcome of the probability. So another school of thought is my favorite scientist, Paul Dirac. So he noticed that the strength ratio of strong interaction force to gravity is proportional, similar to the age of universe. So if age of universe is changing, so is this one. This must change. But there is no evidence for that. There is actually there are search for finding, for example, different constants of nature. If they are changing, then yes. So actually laws of nature are changing, are evolving. But we haven't observed that yet. But I'm sure, I'm just going to put some words in Dirac's mouth. If he was there with us, listening to James Gates talk, he would say, okay, Dr. Gates, That's multiverse is good idea. But if you found computer codes in the fabric of universe, one possible answer could be maybe that's the simplest way that nature can store information. And that's based on Occam's razor principle. So nature finds the simplest way to evolve. Now too much, I think, literature review. Just let me go to my simulation very quick. I don't see the clock, but oh, I'm sorry. So let's just introduce a fictitious system. We have positions, we have particles, so per unit we have a fixed number of positions per unit of volume, and we introduce particles in it. We can calculate the permutation, and that's related to entropy or disorder of the system. Sometimes we have local decrease in entropy. I tell you why, but that we call a structure. And then space-time is actually they follow entropy. So whenever they're going from more entropic regions to less, and then the equilibrium is just when delta S, the total delta S, or the change in disorder is 0. Okay, so and then we can introduce entropic force, which is related to or proportional to the change in gradient of disorder. So that's, I try to explain very. Okay, entropic forces by definition maximize entropy production within the present and future time horizon, rather than just greedily maximizing instantaneous entropy production. Okay, so that's the sentence is important. What does it mean is when you have a system, and so at the edge, the simplest way of increasing the entropy of the system is just at the edge, they're just moving away from each other, but that's not true for the inner layers. So sometimes some of these particles, in order to increase the entropy, so they are affected by their neighbors. So in order to increase the entropy, sometimes they have to get closer to each other. And that, from an observer here in inner layers, it can be seen as emergent effect as force. So an observer sitting right here doesn't know about anything about the edge, just sees, for example, particles getting closer to each other. So local entropy changes results in emergent forces that we observe. I mean, that's kind of obvious, I think. And I think the best example, you can look at the movement of this guy. It's called Slinky Dog. Please do that. It's also the best example I could find. So our simulation, on the boundaries, you can see this the flow of entropy, the maximum change. But the important result I want to show that whenever you have any decrease in entropy in the structures, as I mentioned, that results in an overall increase in total volume entropy. If you remember, I said living organisms, they just release energy to increase the entropy of the system. But here in this fictitious system, what happens is the emergent effect is increasing of the volume entropy. So that, I just exaggerated this to show this effect. These are the conclusions you can read. I'm sorry. So the same stuff, just force emerges as an attempt to reach local equilibrium, entropic force is driving force before, or to reach equilibrium, and evolution happens in the local structures. We haven't reached that point yet to simulate the evolution in the structures yet, but we are so excited about these results. Thank you, my collaborators. If you have any questions, sorry.
Thank you, Saeed. I think in the interest of time, we should just move on to the next presentation. So let's thank Saeed again. Thank you very much.